Alright, exciting day today. Doing one-sided limits. In the final two examples in the previous section, we saw two limits that did not exist. However, the reason for each of the limits not existing was different for each of the examples. We saw that the limit of cos of pi over t as t approaches 0 did not exist because the function did not settle down to a single value as t approached t equals 0. The closer to t equals 0 we moved, the more widely the function oscillated. In order for a limit to exist, the function must settle down to a single value. However, we saw that the limit of h of t as t approaches 0, where h of t is 0 if t is less than 0 and 1 if t is greater than or equal to 0, did not exist because the function didn't settle down to a single number as we move towards t equals 0, but instead because it settled into two different numbers depending on which side t equals 0 we're on. In this case, the function was a very well-behaved function, unlike the first function. The only problem was that as we approached t equals 0, two different numbers depending on which side t equals 0 we're on. As we approached t equals 0, the function was moving in towards different numbers on each side. We would like a way to differentiate between the two examples. We do this with one-sided limits. As the name implies, with one-sided limits we will be looking at one side of the point in question. Here are the definitions for the two one-sided limits. Right-handed limit. We say the limit of f of x as x approaches a to the positive power equals L, provided we can make f of x as close to L as we want for all x sufficiently close to a with x is greater than 0 without actually letting x be a. And we say that the limit of f of x as x approaches a to the power of negative, I don't know how to read that, equals L, provided we can make f of x as close to L as we want for all x sufficiently close to a with x is less than a without actually letting x be a. Note that the change in the notation is very minor, and in fact might be missed if you aren't paying attention. The only difference is the bit under the limit part of the limit, or the LIM part. For the right-handed limit, we now have x approaches a to the power of positive, which means that we will only look at x is greater than a. Likewise, for the left-hand limit, we have x approaches a to the negative, which means that we will only be looking at x is less than a. Also note that, as with the normal limit, i.e. limits from the previous section, we will still need the function to settle down to a single number in order for the limit to exist. The only difference this time is that the function only needs to settle down to a single number on either the right side of x equals a or the left side of x equals a, depending on the one-sided limit we're dealing with. So when we look at limits, it's very important to pay very close attention to see whether we are doing a normal limit or one of the one-sided limits. Let's now take a look at some examples from the last section and look at one-sided limits instead of the normal limit. Okay, so for the first one, example 1, the limit of h of t as t approaches 0 with the plus sign. So this would be looking to the right or anything greater than 0 in that direction. So it says if t is greater than or equal to 0, it's 1. So this is going to equal 1. And for the other one, the limit of h of t as t approaches 0 with the negative, that's going to be 1 because, or no, it's going to be 0 because when t is less than 0, it equals 0. Just in case, I'm going to graph this, kind of. So for 0, the limit is going to be 0. For anything less than 0, it's going to be 0. So we're just just kind of like that. And then when t is greater than or equal to 0. Oh wait, or equal to 0, okay. So it's actually going to look like this. And then when it's at 0, it's going to be a 1. And then so are all these other points. Like that. So from the right, it approaches 1. From the left, it approaches 0. And then we could say the limit of h of t as t approaches 0 equals does not exist, because they're not approaching the same number from both sides. To remind us what the function looks like, here's the graph. So we can see that if we stay to the right of t equals 0, i.e. t is greater than 0, the function is moving in towards a value of 1 as we get closer and closer to t equals 0, but staying to the right. We can therefore say that the right-handed limit is, and that should be what I put. Yep. Likewise, if we stay to the left of t equals 0, i.e. t is less than 0, the function is moving in towards a value of 0 as we get closer and closer to t equals 0, but staying to the left. Therefore, the left-hand limit is 0. In this example, we do not get one-sided limits, even though the normal limit, but we do get one-sided limits even though the normal limit doesn't exist. Estimate the value of the following limits. So the limit of cos pi over t as t approaches 0, positive, and then the same thing but negative. So what did this look like in the previous section? Because I don't feel like rewriting all this. What's this one? 4. I don't even know, man. What is it approaching? I don't even know how to define this. Doesn't look like it's approaching anything. From the graph of this function shown below, we can see that both of the one-sided limits suffer the same problem that the normal limit did in the previous section. The function does not settle down to a single number on either side of t equals 0, therefore neither the left-handed or the right-handed limit will exist in this case. Oh, they don't have to exist either. I didn't know that. So one-sided limits don't have to exist, just as normal limits aren't guaranteed to exist. Let's take another look at another example from the previous section. Estimate the following limits. I gotta plug in stuff for this. Unless this is from the previous section, so I'm gonna look back. Alright, yeah, what's this look like? Alright, so from the right, it's definitely approaching. It's definitely approaching 4. And then from the left, it's also approaching 4. So we're just gonna say it approaches 4 from both sides. Of g of x as x approaches to the positive, that's 4. Limit of g of x as x approaches to the negative, that is also 4. And then the normal one, you already said that's 4, so. Yeah? So as we've done in the previous two examples, let's remind ourselves of the graph of this function. In this case, regardless of which side of x equals 2 we are on the function, is always approaching a value of 4, and so we get 4. Note that one-sided limits do not care about what's happening at the point any more than normal limits do. They're still only concerned with what is going on around that point. The only real difference between one-sided limits and normal limits is the range of x's that we look at when determining the value of the limit. Now let's take a look at the first example, first and last example in the section, to get a very nice fact about the relationship between one-sided limits and normal limits. In the last example, the one-sided limits, as well as the normal limit, existed and all three had a value of 4. In the first example, the two one-sided limits both existed but did not have the same value, and the normal limit did not exist. The relationship between one-sided limits and normal limits can be summarized by the following fact. Fact. Given a function f of x, if limit of f of x as x approaches positive a, limit of f of x as x approaches blah blah blah. Okay, so basically, if it's the number that they're approaching from the left and the right, if they have the same value, okay, then the normal limit will exist, and it equals the same value. Okay, likewise, if the function exists, then the left and right, okay, I can't even, it's harder to say it than it is to understand it. The fact that this can be turned around to also say that if this fact can be turned around to also say that if the two one-sided limits have different values, then the normal limit will not exist. This should make some sense. The normal limit did exist. If the normal limit did exist, by the fact the two one-sided limits would have to exist and have the same value by the above fact. So if the two one-sided limits have different values or don't even exist, then the normal limit simply can't exist. Let's take a look at one more example to make sure we've got all the ideas about limits down we've looked at in the last couple sections. Oh, that's a lot of letters. Okay. This is example 4. So A. Compute each of the following. F of negative 4. It's 2. Oh wait, no, it's undefined because there's a hole. B. The limit of f of x as x approaches negative 4 from the left. It's approaching 2. F of x as x approaches negative 4 from the right, also approaching 2. F of x as x approaches negative 4, it's 2. E. 1. It's 4. F. Limit of f of x as x approaches 1 from the left. It's approaching 4. The limit of f of x as x approaches 1 from the right. It's approaching -2. Guessing the next one's going to be it does not exist. The limit of f of x as x approaches 1 does not exist here. I, f of 6, that's 2. J, limit of f of x as x approaches 6 from the left. 5. K, limit of f of x as x approaches 6 from the right. 5. And then L. Limit of f of x as x approaches 6. It's 5. Alright, let's check the answers. So, -4 doesn't exist. I'm not going to read all this out. 2, 2, 2, 4, 4, -2 does not exist. 2, 5, 5, 5. Okay, I think I'm alright. Hopefully, over the last couple of sections, you've got an idea of how limits work and what they can tell us about functions. Some of these ideas will be important in later sections, so it's important that you can have a good grasp on them. I think I understand limits pretty well, man. So far, there's still limit properties, computing, infinite limits, limits at infinity, continuity, yeah, all that shit. But so far, I'm doing pretty well, I feel like. Professor Leonard 1.2 properties of limits, techniques of limit computation. This is a long one, 3-hour video. We have about 1.2. Whoops.
We gotta start with some basics. Is that 1.2 or 2.2? 1.2. We're skipping a chapter and I was going, uh-oh, we're in trouble now. Yeah, I'd like you to read the rest of chapter 1, you know, just kind of get it, and then we suck. Some teachers do that, I've heard. Anyway, no, we're 1.2, my bad. I just like the number 2, so I thought I'd put it up there on the board, see what happens, you know. We're gonna have to start with some basics. Some basics that we know are truths, and then we'll be able to figure out some properties, use those properties to discover how to compute some limits. So first, little basic here. The limit as x approaches a of a constant c, where c is a constant. What's the picture? What's the graph of a constant? Show me with your hands what the picture of it. Sure, yeah, exactly. What is it? Yeah. What's the picture of a constant? Of a function equaling a constant? Yeah, it's not this way, right? It's this way. That's a constant. It doesn't change slope-wise. The slope is 0. It just goes straight across. True? So if I were to draw the picture of this, You would agree that that would be my function, right?
Okay, so it would have to be C, right? Or is it does not exist? It's either it does not exist because of like some weird technical reason, or because it's C like always. So.
Right? Well, here's the cool thing. If I take a limit at any point whatsoever, so for instance, here's my A. Here's my A. I just picked a random point, doesn't matter what it is, okay, it's arbitrary. What's the limit as we go from the left and the right? Firstly,
C,
is
right?
it the same thing? Yeah, it's not gapped or anything, it's going to the same thing. What's the limit as we go from the right? What's the y value as we approach the a value? C. How about this way? So the limit is? C. What that means is the limit of a constant is the constant itself. That's cool.
Nice.
Where C is a constant. That's nice, right? That makes sense graphically. We just kind of interpret it. So every time we take a limit of just a number that's a constant, we just have the constant. That makes things nice for us. Number 2. How about the limit
It's X.
of x as x approaches a? So what's the graph of just x, like y equals x? How's that look?
It's just should be like this, right? Or wait, hold on. Wait, hold on. I gotta think about this. So 1, 1, 2, 2, 3, 3. 1, 1. Oh wait. Wait, it's like this, I think. Maybe?
It goes through the origin, great, because the slope would be 1 and the y-intercept would be 0.
Oh, okay.
So this is just...
Wait, that would be... The limit of x as x approaches a. It'd still be x, right?
If you show me your hands, how would it look? Yeah, just like that. Not like this, but a diagonal. Now I'm going to pick another arbitrary point A. The question is, if this is y equals x, just our diagonal line, if you plug in A to
Yeah, it'd
y
have to be
equals x,
x.
what do you get out of it? Yeah.
Oh wait,
No.
a.
A, true? You plug in 2, you
Okay,
get
no,
out 2,
it'd be
plug in
a.
3, you get 3, plug in 4, you get out 4. You with me on that? So my question is, as x approaches A from the right and from the left, what's the y approach from the right
A.
and from the left? It approaches A. So from the right, our function, the y value is going towards A, true? From the left, the y value is going towards A. Does the limit exist? It's the same from left and right, and it's equal to how much? Cool. So here's 1. Here's 2. It says the limit, this is really interesting. It says the limit of a like x, just a simple function like this, is the same thing as if I were to just plug that number in. So if I'm taking the limit of some function x at some point a, the answer is just a. That's it. That's kind of nice, right? Why? Well, because graphically we can see that. Last one. Amazingly, with this stuff, we'll be able to do everything else. It's kind of cool. This, I'm just going to write it out because we just covered it a second ago. This is why we covered it a second ago. How much is the limit of 1 over x as x approaches 0 from the left-hand?
Let me think. So we got 1 or 0 is an asymptote. 1, 1, 2, 3, wait, hold on. 1, 1, 2 half, 3 third, negative 1. It'd be like, it's this thing. Crap. It's this, right? So, approaching from the 0 from the left. I'm gonna say it does not exist because it's not, as it's going up forever, it's not picking like a certain number to like approach. Same from the right. That's my guess.
Inside was on the board just a couple minutes ago. How much is that? Negative. Very good. Negative infinity.
Oh, infinity.
How much is the limit?
No, that makes sense. I was thinking either infinity or doesn't exist because it's not picking like a specific number, but he did do that on the other video. Forgot.
Of 1 over x as x approaches 0 from the right hand side. What was
Or wait, this goes down, doesn't it? Wait, -1. -1, -1. Yeah, this goes like this. Oh, wait, never mind. Dang it. It's like that.
What was that? Now, last thing we're going to do today. Firstly, are you okay with these 3 basics? Okay, these two. This one we already knew. These 2 are kind of interesting. They're really unique, and we're going to use those to solve some limits here in just a bit, to evaluate some limits, I should say. Before we do that, though, I got to tell you the properties of limits. We're going to leave it at that for today, and I'll show you how to apply these next time. So basic properties. We're going to assume that we have 2 functions. And that the limits exist for each one. So the limit of f of x as x approaches a exists. The limit of g of x as x approaches a exists. Notice please, that these limits are, that the x is approaching to the same exact value. You see that? The a is the same. It's got to be the same for this really to work, okay? So it's got to be the same approachment. I just made that word up. I don't know if it exists. But you got to approach the same number. Here's your properties. There's basically 5 things we can do. They're all quite interesting. First one, this is why both of those have to exist, is because we're going to do this. If you have a limit, you're not going to see why this is really interesting until next time, so make sure you come back on Friday. If you have a limit where you have a function inside of it added to another function, no matter what that function is, you can separate that function. So for instance, you can do the limit as x approaches a of f of x plus the limit as x approaches a of g of x. That's legal. You can separate limits by addition. It's kind of neat, right? By the way, this is why you had to have the same letter here, because we have to do that. And you can also combine them. That's legal to do as well. So these are not one-way streets. Let's see. I'm going to make this a little bit easier for us. I'll not write the second one. I just need you to know that this works for addition and subtraction. That makes it nice. It also works for multiplication. You can separate limits by multiplication.
This reminds me of logs, log properties.
So that's legal to do. You can also separate them by division, which means if you have limit as x approaches a of f of x over g of x, that's the same thing as the limit of f of x over the limit of g of x. That's true, but you have to have something. What can't this equal? You can't have that. So the limit of g of x cannot be 0. Last one, the one that I find the most interesting. This is really cool. I know we're a minute or two over. Sorry about that. If you have a limit raised to some power, some function raised to a power, this is the coolest one. You're going to see why in next time. But you can actually do this. This makes it so you can do a limit of the function and then raise it to the power. That's a neat one. That means that you can remove an exponent from your function with limits. That's very cool. What's fascinating about this is it even works with this. Because that is an exponent, right? A radical is an exponent. You can remove a radical. I'm a bit leave it like that. You can take a radical outside of your limit. We're going to do many examples of those things, but have those written down. We'll start with that next time. Well, if you remember from last time, what we're talking about is limits, and I think the last thing I did leave you with was the properties of limits. And there's a few is limits, and
I'll watch till he changes his shirt.
I think the last thing I did leave you with was the properties of limits. And there's a few things that we can do with our limits. Now one thing we knew was that from our basic limits, our little bases up there, the limit of a constant equals that constant. That was real nice. Also, the limit of just a simple variable like x equaled whatever the x was approaching, that number. So those are the two basics I gave you. And then I gave you some properties. Basically, with our properties, it says you can split up limits by addition. You can split up limits by subtraction. You can split up limits by multiplication. You can also do it with division as long as the limit of the denominator is not 0. You can also, this is the coolest one I think, anytime you have a function taken to a power inside of a limit, you can take a limit of the function and then take the power afterwards. So that means you can really alleviate the problem of having an exponent within any limit. Are you ready to see how we can do that to evaluate that limit without...
Yes, sir.
doing those silly, like, check 2 in the middle and then find out from the left and from the right. Remember doing those, right, those tables? We don't want to do that anymore. We want to use the properties and our basis for limits to be able to solve this thing. You ready to do it? So here's what we can do. If we look at this thing and say, okay, limit as x approaches 2 of this function, the first thing I know is that I can separate limits by addition and subtraction. You with me? So what this says is, okay, well this can become the limit as x approaches 2 of x cubed minus the limit as x approaches 2 of 2x plus the limit as x approaches 2 of 7. Now, a lot of people are going to ask, do I have to put the limit as x approaches 2 every time? Yes.
Okay. Yeah, this reminds me of a lot of properties of logs.
Yes, you have to do it. It's like asking someone to take the absolute value. You have to write absolute value until you actually take the absolute value of something. So you have to keep on writing limit until you actually take the limit. If you don't, well, you're saying you've taken the limit, and that's what it was. So and that's not a true statement. So you have to write the limit as you're doing these problems. Now, let's use those other rules. One other rule said that anytime, this is the cool one, rule number, property 5, says anytime you have a function to a power, what I can actually do is take the limit of just that function and raise it to the power later. That's true, you can do that. Means I can take the limit of x and then cube whatever that happens to be. Another thing said that I can separate two limits by multiplication. So this would be the limit of 2 times the limit of x. Plus, that's already a constant. We'll deal with that in just a second. How many people are okay with this so far? Do you see what we've done with these properties? We've actually broken up a pretty intense polynomial into limits of constants and limits of just x terms.
Oh,
Have you seen that? What's interesting is I want you to think about this.
Let me try this. Okay, so we're right here. This is a constant. So this would just be 7, right? Let me look back up here. Did I write that down? Yeah, limit of a constant as x approaches a equals that constant. So this is 7. The limit of x as x approaches 2. That'd be 2, right? Yeah, because this is basically x equals y. Meaning when you choose an x, which is a, the y has to be a, so it's a. Okay. So this is 2. This is 2. And this is This is 2 cubed, so 8 minus 4 plus 7, 4 plus 7, 11. Oh wait, limit? Oh wait, no, we just say, or can we write this out as the limit of x cubed minus 2x plus 7 as x approaches 2 equals 7. I think that's the answer. Let's check.
Can you do this for any polynomial? You can always separate by addition subtraction, right? You separate term by term then. Can you always take out exponents? Yes, yes you can. Can you always separate multiplication?
That's kinda cool,
Absolutely.
actually.
So you could do this with any polynomial. You follow me on that
Its
one?
properties are
Well, now check it out.
OP-ed.
Since we've broken up into such simple components, you can now use those there's only two basics. Use those two basics to actually evaluate this limit. Can you tell me what's the limit of x as x approaches 2? It was one of those basics that I gave you. I drew the pictures of them. It said the limit of x as x approaches a was a. It said the limit of c, no matter what, was c. You with me on that? So the limit of a constant is the constant. So the limit of x is a, whatever it's approaching. So y'all tell me now, what's the limit of x as x approaches 2? It's just 2. Yeah, 2. And then I can cube it. Minus, oh, how about this one? What's the limit of 2? Doesn't even matter what I'm approaching, but what's the limit of 2 as I'm approaching 2? The limit of a constant is the constant. So what's the limit of 2? It's 2. It never changes. 2. Times. How about this one? What's the limit of x as x approaches 2? 2. It is 2. Plus, what's the limit of 7? No matter what you're approaching, what's the limit of 7? You with me on the 7? It's a constant, yeah? So we had those two basics. The limit of a constant is simply the constant itself. It's a horizontal line. The limit's always going to be the same. It's just 7. Can you add that together? How much is it?
Oh wait. What'd I do? I said set. Well, I didn't. Bruh. I couldn't do 4 plus 7. 4 plus 7 is 11, dude. Jeez, man. It's not good.
8 minus 4 plus 7? Looks like 11 to me. Did you get 11 as well? That means we've just calculated our very first limit without doing tables and without looking at graphs. We're able to do this. Now, can I ask you to do one thing for me, please? Just check this out. Can you go ahead and just in your head or off to the side, take this number 2, plug it in there, and tell me what you get. Can you do that for me? What's f?
8 minus. Oh wait, it's gonna be 11, isn't it? 8 minus 4 plus, yeah. Because there's no whole or asymptote on this quadratic. So see, it doesn't have to it can just exist there, I guess.
Book 2.
It's still a
Wait,
limit.
say that again? 11. Did y'all get 11 when you plugged in 2? Wait, that's weird. Is that a coincidence? No, it's not a coincidence, because here's what we can do. Oh, not 2. Sorry, 11. It says, well, if you can separate a polynomial into its terms and then its individual components raised to powers and multiples like that, essentially all you're doing is plugging in that number for those spots, for your spots of x, right, for your variables of x. Basically, you can do that here. So here's what I'm going to say. You already determined, I already asked you this, whether this would work for every polynomial. You said that it would it? Or wouldn't it? Can you do this with every polynomial? Polynomial are things that looks like that. Can you do it for stuff like that? Absolutely. You can always separate them. Take powers outside, break it up into a constant times a variable. That means that to find the limit is an important thing. To find the limit of any polynomial, all you have to do is evaluate that function at the point A, whatever that is. This is going to work for every polynomial. So this idea works for every polynomial.
Is point A always given?
Oh yeah, yeah.
So it's never, it'll always be a given in the, for initially.
Yes, this number is always given to you. has to be given. Works for any polynomial. In plain, and mathematics, I'll say it in plain English in just a bit. Here's basically what all this stuff says. It says that the limit as x approaches a of some polynomial. Do you understand the notation? The limit of a polynomial, that's a polynomial, as x approaches some number is equal to p of a. What's p of a say? English in just a bit. Here's basically what all this stuff says. It says that the limit as x approaches a of some polynomial. Do you understand the notation? The limit of a polynomial, that's a polynomial, as x approaches some number is equal to p of a. What's p of a say? That's exactly right. It says evaluate the function at that point. Basically, here's what it says in English. To find the limit of a polynomial, just plug in the number. That's what it says. Can y'all do that? Oh yeah, that's great. It says to evaluate the limit of a polynomial, plug in the value. To find the limit of a polynomial, just plug in the value. Which is 8 in our case. You want to see a few more?
Yes,
Yeah. Hopefully you're not like, nah, done. Forget all the hard stuff. Just leave it like this. You want the hard stuff, don't you? Yes. Not really. But yes. Limit of x to the fifth minus 3x plus 4 all to the third power as x approaches 2. That's what we're asking here for. Now the question is, could you, if they wanted you to, could you go through this whole process and do the same thing? Yeah, absolutely. You can pull out that 3, that power 3. You see it? You can separate all the terms. You can separate out that power 5. You separate the 3 and the x, plug in those numbers in those 2 spots, and it would be essentially just a valuation of that. So how can we figure out this limit? Just plug that number. Why don't you do that on your own? Plug that. That number in there, substitute that in there, because we know that the limit is going to equal whatever this function is with evaluated at the point a equals 2. Was it 30 to the third power or something like that? 27,000. 27,000. How many people got 27,000? 20, is it 27,000? Yeah. I hope so. Not everyone raise your hand. Are you guys okay on how we got those numbers? I need to know. If you're not, then I can re-explain it. But nudge your head if you're okay on how we got those numbers, the 27,000. Yes? So do you see that what we're actually doing is saying, okay, I know this limit is the same thing as evaluation when I plug in the number 2 and then cube it. 32, 3. Yeah, I know I have too many 2's. 32 minus 6, it's like 26, plus 4, that's 30. Take 30 to the third power, and you get 27,000. You follow me on that one? Yes, okay. And that's exactly what that means. Hey, you just evaluated first limit. Don't you feel proud? No? Oh, well, you're gonna.
You get a plaque?
Sure. Eat a bunch of candy, you get lots of plaque. Get it? Get it? That's a joke. Plaque versus plaque. Oh, it's so, whatever. I know. By the way, not all of our limits go to 2. I'm just using 2, so you know. What about that? Now, is that a...
That would be negative 17. It's still a limit.
The answer is no. No, that's a rational. That's a rational function. Is it a polynomial? But could you still do the same basic thing? And the answer is yeah, you can, because of, I think it's rule number 4, or your property number 4, 3 or 4, one of those things, which says that you can actually separate your division, can't you? Provided that your denominator is not what? Will that make the denominator 0? Will this point make that 0? Then you're fine. Then you're fine. You can do that. So because we can do this whole step, this is the limit as x approaches 2 of 4x squared plus 1 over limit as x approaches 2 of x minus 3. Well, now look at it. Is that a polynomial? Yes. Is that a polynomial? Yeah, they're both polynomials. That's a polynomial and that's a polynomial. So this says you can evaluate that by plugging in 2, and you can evaluate that by plugging in 2. The only thing you got to check for is that the denominator is not 0, which we already know, right? It can't be 0 on the denominator. That would be a problem. So do you need to show me this step? No, no. Just plug in the number. If it works, then you're okay. If you have 0 on the denominator, then you're not okay. Okay? Do you get the idea, though? Do you see that we can separate division? Provided that this number does not evaluate that polynomial, make it 0, then that's fine. So we're going to separate that. We don't have to actually show this part. It's just I'm showing you once that it is true, because now it makes it a polynomial. It makes it a polynomial, and we know from here, hey, you can evaluate a limit of a polynomial by just substituting them in that number. So therefore, we can do it here. Have you substituted that in yet? So it's going to be 4 times 2 squared plus 1 over 2 minus 3. 17 over negative 17? Notice how here I have to write the limit, here I have to write the limit, here I have to write the limit. As soon as you evaluate, you don't write the limit anymore. Do you guys see the difference there? So yes, you must write the limit until you actually evaluate it. Once you do that, you're done. No more limits. You just have those numbers, but you have to write it up until that point. Question?
Say that x was approaching 3. Would you still be able to...
I'm so glad you asked that question. Can I answer that?
No, then you have to use the properties.
In like 30 seconds?
Okay.
Okay, cool. Love those. Don't you love it like when you're thinking about something and you're going to make your next point because you're a teacher, you know, that's kind of cool, you want to do. And then someone goes, hey, what about this? You're like, oh, that's my next point. Don't you love that? That doesn't happen to you. It happens to me all the time, which I love that. Actually, it's going to be 1 minute and 45 seconds. All right?
Do you have the time on that sheet of paper?
Maybe. I'm not OCD. How about that one? Is that?
That'd be 6 to the power of 3.
A polynomial. Please shake your head no. No, polynomials look like this. That's it. That's polynomials. No roots, no denominators. That's polynomials. So this is definitely not a polynomial, but I want you to see what you can do. Do you see that you could pull the cube root out of it? Once you did that, you could separate by division like we did in this problem. So essentially, anything will work provided you plug the number in and you don't have any domain issues. So basically, if you plug this in, it doesn't make that 0, you're fine. It doesn't make, well, actually, that's a cube root, it doesn't even matter. Cube roots, you can plug in any number, that's fine. So provided that's not 0. If you plug in 1, does this denominator go to 0? No. Then you're fine. Why don't you go ahead and plug in 1 and see what we have. Notice I have my limit here. We could do all this work, right? We could separate the cube root. We could do that. We could show that. We could separate my limits by division and show that as well. But you just need to know that we can plug in a number into a rational or any type of problem that we have, provided that we don't have that denominator 0 and don't run into any domain issues. So if we plug in that value of 1, we get the... Do we still have a cube root? Yeah. Don't forget about the cube root. How much does that give you? Well, if you're going to say it, say it. How much does it give you? Cube root of 6. Cube root of 6. Raise your hand if you're able to get the cube root of 6. Okay, I'm 10, 12 seconds over. Now, let me show you this problem. Firstly, do you have any questions on the whole polynomial idea, breaking that up? Any questions on what we're allowed to do over here? We're allowed to evaluate limits by just substituting numbers, provided we don't run into any problems. Problems would be 0 on a denominator, or things that don't validate our domain. That would be a problem. I'm sorry, invalidate, or that don't invalidate our domain. I think this is now going to answer your question. In every previous problem, we were able to just substitute in that number into our limit because we knew we could break it up into forms of polynomials or basically, because they're polynomials, powers with individual x's multiplied by constants, right? So we could do those limits. That's why we were able to do this stuff, is because we could have shown all that breaking it up and just evaluated constant limits and limits that just had x's and then taken the powers later. The only difference with this one is, if you try to do that, if you separate this by division, the numerators can work just fine. Because you're going to get how much on the numerator? It's a polynomial, right? You get 0. Is it okay to have 0 on a numerator? Sure. Yet on a numerator, yes. Now, what would happen, though, if you try to substitute in this 2 down here?
Undefined.
You get 0. The limit of your denominator would be 0. Is that a good thing to have? No. That's a problem. We can't ever have that.
So now you gotta use the properties. Oh, I'll try that right now. That is property, right? Okay. Okay, limit of 4 is x approaches 2, it's 4. Limit of x is x approaches 2, it's 2. Limit of 2 is x approaches 2, it's 2. Still 0 though. Still 0 on the bottom. Because you can't. Okay. It's harder than I thought. Yeah, then how do you use the properties to evaluate it? You know, I want to erase right now, I guess. Wait, did I erase the whole thing? Jeez. Alright, whatever. I'll see what he does.
What do we do?
The top is the difference in squares.
The top is a difference. So wait a second though. Are you saying that if I do this, I know y'all know a difference of squares, right? What's it going to factor as? Are you saying that I should be able to simplify those out of this expression? Well, wait a second. Wouldn't we be simplifying out a domain issue?
No, because you just care about what's happening as you approach it.
You're not actually gonna
Wait.
ever get to that point.
Say that again. Say it
You're
loud.
not gonna actually ever get to the point 2 on the graph.
So are we simplifying out a domain issue? No, he's exactly right. Are we actually getting to the point 2? No. So really, this is kind of weird, but with a limit, we're technically not making any mistake here. We're not actually getting to 2. But we're actually getting to that point. So when we look at this, we go, oh, okay, we could just simplify that out. We're not simplifying out a domain problem because none exists, because we're not actually getting to 2. You just can't evaluate the limit by plugging it in because according to this function, yes, you will at that point. That's the difference between polynomials that don't have issues and things like this that do, that have domain problems. If you're trying to find the limit of this guy as you're going to 2, well, there's a problem with that. There's a hole there, right? Do you recognize firstly that there is a hole and not an asymptote here? What was the difference between a hole and an asymptote according to the algebra? Oh, you better know. You gotta know that. Say that louder. You're right. Asymptotes don't factor out. Holes do factor out. Do you remember that? So if you can simplify it out, that's a hole. If you can't, you have some sort of asymptote. So in this case, yes, we have a hole. That means that if you have a hole in your graph, can you actually find out where the function is at that point? You can't even do it. It doesn't even exist. So we have to do limits to find that out. But in order to do that, we do have to simplify this function. We can factor, we can simplify because we're actually not getting to the 2. This is okay. It's okay because x never equals 2. Never gets there. Really close? Yes. So what we can do now is say, all right, then this, according to the limit, is exactly the same thing as that. Is that now a polynomial? Sure. Can you plug in 2? How much are you going to get? 4. Just 4. That's kind of neat, right? Oh, that should be amazing to you. Be like, yeah, we can simplify this stuff out because we're not actually getting there. Therefore, we change these weird-looking holy functions, not because they happen on Sundays, but because, you know, we have simple. And then we can just plug in the numbers, and now it's a polynomial, and we're good to go. So if you can factor and simplify, then you can find the limit. Does that make sense to you? That's awesome. A few more?
Okay.
We're going to make them a little bit more advanced, a little bit more advanced, so by the end of the day, we'll have some pretty unique things going on, okay? Now, before you get all crazy and start factoring everything that you see, you might want to just check that point and see if it's even a problem, all right? Because sometimes they might give you that stuff, and there's no issue. It'd be like...
Alright, is there an issue? Let's see. 16 plus 16 minus 4 minus 12. There is definitely an issue. Factor out at 2, x plus 4, x plus 4, x minus 4. There's still a plus x there. What up? X. No. Wait. X. X plus 1 minus 12. No. Wait, you can do this. X plus 4, x minus 3, right? Squared minus 3 plus 4 minus 12. Okay. 2 over x minus 3. Plug in the negative 4. Negative 2 over 7. So the limit of 2x plus 8 over x squared plus x minus 12. As x approaches negative 4, it's negative 2 over 7.
This example, this would have an issue if we were going to the limit of x equals, or x is approaching 3. Wouldn't that be a problem? But we're not. We're going to 2, so there was no problem here. So at least check and make sure you actually have a problem before you start factoring things out. Make sense? So try it. Do I have a problem if I try to evaluate at negative 4?
Yes.
Yeah, I do. I get 0 over 0, right? That means you should be able to factor. Hey, if you get 0 over 0, I told you this was the property of mathematics. If you get 0 over 0 when plugging the same number, that means x minus that number is a root. That means somewhere over here I can guarantee you're going to have an x plus 4. Because x minus negative 4 is x plus 4. This will be x plus 4 times something. This will be x plus 4 times something. And then we should be able to simplify out that problem.
Wait,
Once you try
what?
this mathematics, that means you should be able to factor. Hey, if you get 0 over 0, I told you this was the property of mathematics. If you get 0 over 0 when plugging the same number, that means x minus that number is a root. That means somewhere over here I can guarantee you're going to have an x plus 4. Because x minus negative 4 is x plus 4. This will be x plus 4 times something. This will be x plus 4 times something, and then we should be able to simplify out that problem.
Oh, okay, I see.
Why don't you try that right now? Factor that. I want you to
Sure.
simplify it, and then see if you can evaluate the limit
I'll
of
give
what
you
you
some.
get out of that. Should be your quotient, I suppose. Did you factor? Was there an x plus 4 like I magically predicted? I love when that happens too. So if you were to factor this out, by the way, have you noticed that when you're factoring, you still must have the limit notation? Do you see that on the board? You've got to have limit. Look at, here's a limit, here's a limit, here's a limit. When did I stop using limit? When I finally actually was able to plug in the number. Do you see that? You must have a limit. I will mark you off points if you don't have those limits. If you go, I'm going to write this limit, but not that one, I'm just going to get my answer. That's not how limits work. If you say you don't have a limit here, you start crossing stuff out, and then you magically plug in 2, you've made a domain issue. If you're with limits, that's okay. So you have to say, I'm working with limits here until you get down to this point. Do you see the point? All right. So we still have a limit. By the way, that's going to be annoying, I know, because you're going to have lots of steps in some of these limits, but you need to do it. We're going to factor We're going to factor. See anything that simplifies out of our problem? Now, some of you might be asking, well, wait a second. Don't I still have a domain issue? Because if I plug in 3, I have a problem. Don't I still have a domain issue? The answer is, well, yeah, sure, at 3, but are we trying to figure out what's happening around 3? I don't care about 3. What point am I trying to figure around? Yeah, so I've gotten rid of the problem. Because as soon as I cross out this x plus 4, now when I substitute in -4, it's no longer an issue. Can you now evaluate at -4? Let's go ahead and do that. Notice how I've written limit, limit, factored limit still, and now I can put, well, this is going to equal 2 over -4 minus 3. I've now evaluated my limit. I don't write the limit notation any longer because I don't have any more variables. As soon as you substitute in for your variable, that is your limit. And we get -2/7 as our limit. How many people got -2/7 feel okay with this? Is this understandable? Do you guys starting to get the concept of working with this stuff? It's kind of interesting, isn't it? What you can do. I hope it's interesting to you. Oh, I already have it up there. Cool. All right. Oh my gosh. What are you going to do first, do you think?
Let's see, 25 minus 50, -25 plus 25, okay. So, definitely a problem. So factor. Wait, first let me plug it on the top, see if I get a hole. 25 minus 15 minus 10, okay. So it's definitely a hole, so it's gonna factor. And x minus 5 equals 0, so probably gonna get x minus 5 somewhere. And then x plus 2 x squared plus 2x minus 5x minus 10 x minus 5 x minus 5, yeah, x squared minus 5x minus 5x, okay. So x plus 2, the limit as x approaches 5 of x plus 2 over x minus 5, 7 over, oh, okay, I see why you picked this one. There's still a problem. Okay, I'll wait for him to explain that, because this would be the same thing as if I was trying to solve for an asymptote, which I tried to do earlier and it didn't work.
But before you factor, don't get crazy on factoring. What are you going to do?
Check.
You're going to check it. Yeah, check the 5. Because if it works, well, there's no reason to factor it. That would just be a waste of time. Probably confuse yourself too. Like, wait, nothing simplifies. Oh no.
True.
Now, if you try the 5 here, do you have a problem? Okay. So if you do have a problem, then what do? Now you factor. So if you haven't factored already, go ahead and factor. What's the top one factor as? Plus 2 minus 5? How about the denominator? What have you got there? Oh, minus 5, minus 5. All right. Did you all factor it correctly? All right. Thank God. Good. At least we factored it correctly. Do you see anything that simplifies? Wait, not both x minus 5s? One x? So we go here and here, yes? And what we get out of this is an important example for you to see. You get x plus 2, x is still approaching 5, x minus 5. Try to plug in the 5, what are you going to get?
0.
You're going to 7 over 0. Is that still a problem? Yes. Oh, man. So wait a second. What do you do if you still have a domain issue on this thing? I've now given you 2 cases. I've given you cases where the problem, the domain issue is a hole. Do you see that? It's a hole, and you can get rid of a hole. It's a removable discontinuity, and you can find the limit of that. It's very easy. You factor it, and then you evaluate. Now, I've also given you another case where not only do we have a hole here, we actually have, what is that when you can't simplify out the domain issue? That is a vertical asymptote. So now we have this issue. What are we going to deal? How are we going to do that? Well, this is where you're going to use what's called a sign analysis test. Listen, you really do have to comprehend that if you can get a 0 over 0, like you did over here, you're going to be able to at least factor it and simplify something, right? Sometimes, as I've shown you, it will get rid of the problem area, and you can just substitute in a number and be just fine. That happened here, and that happened here. Not sure if you're okay with that one. Now, other times, sure, we got 0 over 0. We factored it, we got rid of what looked like a problem area, and it was. That's like a hole. However, can you get rid of this x minus 5 in any way whatsoever?
No.
If you can't, what was that called again? It's asymptote. What you have to do is sign analysis test. Here's what you do with a sign analysis test. You put the numbers that will make the numerator and the denominator equal to 0. Put that on a number line. What numbers am I talking about here? 5, definitely. 5, because we want to find out what's happened at 5, and that was our problem area. So 5 is going to have to go over here somewhere. So far, so good? Now, what else do we need? Now, -2 is interesting. We don't really need it because really we're looking at this area. However, we need to know what happens between this range. You see, what you're going to do is called a sign analysis test, and that means you're going to find the sign in this interval and a sign in this interval. The only reason why we need this number is to make sure that you pick something in this range. Because if you don't, if you pick something in this range, this is where the signs change from positive to negative. Does that make sense?
Wait. Yeah, because if you do -2.1, then it's going to be a negative. So the sign changes.
So you have to find something in this little range and this range over here. It could be anything over here. But in this range, it's got to be between these 2 numbers. That's why we put the -2. We're not taking a limit to -2. We don't care. Really, we don't care. We want to find out what happens at the 5. Is that clear for you? Scott?
Are you talking about like the trig function sign?
No, no, this is easier.
Okay.
There's no trig functions here.
Okay, so I was thinking the same thing. Trig function sign, I'm going, okay, let's see how we're going to get there.
Where's these trig functions coming from? Darn it. I hate calculus. No, there's no trig functions. This is basic. Okay, this is just plugging in some numbers. Sign, as in I am signing. Okay, sign, like yes,
That's why they were
sign.
confused, like, so
Sign.
it's like a sign.
Like sign. Oh, I get it. Sign like sin. No, we're not sinning. We're signing here. No, we want the sign. Let me write that. Sign analysis. Analysis is another one of those things you can't really abbreviate that well. Analysis. Got it. The sign analysis. That'll go viral on YouTube. That'd be awesome. So again, the reason why you have to have the -2 is because your sign will change in these 2 intervals. And we don't care what happens here, but we want to make sure we pick the correct number for this interval. We don't want to be picking -3 because it's going to give us the wrong interpretation of what happens around this. Now, you have to know what happens around the 5. And you already said it once or twice before. Is this a hole or an asymptote?
Asymptote.
It's an asymptote because I can't get rid of it. You follow? So you know for a fact it looks like this. You know for a fact that you have an asymptote right here, right? So you're going to be in one of 4 situations. Watch carefully. You are either going to be going like this, true? Or like this, or like this, or like that. It's one of those 4 situations, and the sign analysis will tell you what it is. Here's how you do it. I want you to take a number in this interval. What's a good number in this interval? Pick 6. You can't pick 5 because, well, obviously you can't pick 5. Pick 6. Plug in 6 and tell me what you get.
1. Oh, positive 1.
Plug it in.
Not the original, but it's not 5.
No, you know what? What you've done here is you've just simplified out a whole. It's going to give you the same exact
Oh wait, like actually
answer.
plug it. Okay.
So
7. 7. Right. Or wait, no, 8. Plug in a 6. Out of 5. Yeah, 8.
plug it in here. What'd you get?
8.
You got 8 because you did 8 over. Wait, what'd you get?
6 plus 2?
Oh, right. 8 over 1. 1. So 8 over 1 is positive 8. That's what I'm looking for. I really don't care about the value. I care about positive or negative. What'd you get? Positive or negative? Make sure you know how to deal with your signs. Okay? So you got a positive. You know what that means? If you got a positive, are you going to be going down to negative infinity or up to positive infinity? Definitely positive infinity because you're doing positives here. You know it's an asymptote already. Somehow you're going to be looking like that. You okay with that so far?
Yeah.
Okay. Now, try another number in this interval. Again, the reason why we have the negative 2 is to stop us from going too far.
Okay. 4. So 6 over negative 1, negative 6, negative.
So what's a number in here? Pick a better number than 4.
0.
Pick 0. 0 is a great number. It's an interval. So plug in 0. What'd you get?
Negative
2 over negative 2. So is it positive or negative?
Negative.
Am I going to be going up to meet that other asymptote at infinity? I'm going to be going. I don't really care how the graph looks. Honestly, I don't. I just really care what the asymptotes are, what the function's doing around the asymptote, because that's what the limit is. What's it doing around the number? Do I need to plug in a number over here past negative 2? No, this is just to stop me. So you got to tell me, does the limit exist, because we're talking about 5, does the limit exist at 5 or not?
No.
If it did, they'd both be going up or they'd both be going down.
True.
Okay, if they're like this, then that doesn't exist. But this is how you show that it doesn't exist. You don't just automatically go, I can't do it, does not exist. Okay? Because you could be wrong, all right? It happened before. It does not exist because you showed it with your sign analysis test. So on your test, when I give you a problem very much like this, which I will do, and I ask you to show your work, or I might even say show a sign analysis test, that's what I'm talking about. I need you to prove to me that that limit does not exist. So if they say show the limit doesn't exist, that's it. Okay? If the limit does exist, you'll be able to simplify out the holes. If it doesn't exist, well then you have to show a sign analysis test. Show that you have an asymptote and it's going like that, or some other way that you cannot make those things go together. How many people understood that? What we were just talking about? Good, all right. A couple notes for you, so I'll write this out so you can remember it later. First one. If you get 0 over 0, what that means is you have a common factor at that point, x minus that point. So if you get 0 over 0, what you're going to try to do is factor and simplify. Factor and simplify. 90% of the time that's going to work just fine. That's these examples over here, all right? The other percent of the time, let's say you factored, you simplified, you still have an issue. So that's number 2. If you cannot simplify the problem, okay, if you can't get rid of the problem, if you can't, we'll say it this way, if you can't cancel the problem, because y'all love the word cancel, right? If you can't cancel the problem, that means it's not a hole. If you can cancel the problem, it's a hole. If you can't cancel the problem, that means you have an asymptote at that point. What you're going to need to do is evaluate it with a sign analysis. So two situations. Holes, cancel them. Great, done. not holes, those are asymptotes. Sign analysis will show you what that does around the asymptote. If they go into the same thing, it exists. Positive infinity or negative infinity. If it's not, then it doesn't exist, and that's the only way you can show that for us. So if you cannot cancel the problem on the denominator, check with sign analysis because the limit might not exist. Because the limit might not exist. How many people feel okay with what we talked about so far? 4 minutes? Okay. I'm going to show you a couple more very unique examples. We'll talk about those. Things you really have to know exactly what to do when you see them. So I want to make sure you see them.
I started writing in all caps thanks to you.
You're welcome. My handwriting is so atrocious. That means bad. So condescending what I just did to you. That's horrible. Sorry. It was really bad until I started writing in all caps, and now I have trouble even writing limit like that. Also, my dad was a carpenter and a draftsman, and so he used all caps all the time, so I wanted to be like him. So I started doing that too. He's much better at it. All right, now, we got this situation here. Limit x minus 1 over square root of x minus, oh my gosh. Well, the first thing you try to do is what?
Alright, plug it in. It's a problem. Factor. Well, let's see. You can't, I don't know how to factor and simplify that. Oh,
Try to plug it in. Do you have an issue?
Yeah.
Now, you have 0 over 0, true? Unfortunately for us, these aren't easy to factor, right? You probably do have some sort of factor out of that, but it's not easy to do. Polynomials are easy to factor, that's fine. But with this, that theorem really doesn't hold that much water because it's not easy to factor that. So, okay, what are we going to do? Any ideas? Have you ever heard of the conjugate? The conjugate is those two terms with a different sign in the middle. If we do that, that's one way you learn in your intermediate algebra course on how to rationalize a denominator or rationalize a numerator or basically just rationalize out a square root. So if we do that, that might help us.
X plus X minus square root of X minus 1, or wait, no, X times square root of X plus X minus square root of X minus 1 for X minus square root of X minus square root of X plus 1. that's kind of a problem. I don't know, man.
So don't forget the algebra that you know. Sometimes we can rationalize. If we do, we'll rationalize square root of x minus 1. Oops, sorry, plus 1 over square root of x plus 1. You have to use the conjugate though. If you don't, well, then you're going to just make your problem worse, because you're not going to get rid of the square root. It's going to be within a middle term of your problem. So you have to alternate those signs. You guys okay with that?
I did something wrong. Oh, I did plus 1 minus 1 on the bottom when I do that. That's why it didn't cancel out. Redo this. I forgot to put the limit. Two squares of x plus minus 1. Crap. Wait, is there a problem now when you plug it in? No. So maybe that's what you do. Two minus 2, 0. Oh wait, hold on. Actually, I'm not going to copy it, that's a lot more work.
You sure? So use that conjugate. Now let's see. Of course we have parentheses here. Now I'm going to give you a little piece of advice. Generally, you don't want to distribute, in this case, the numerator. If you were rationalizing the numerator, you wouldn't want to distribute the denominator, because ultimately you're trying to simplify out something. Are you with me on that? You're trying to simplify that out. So I'm purposely not going to distribute the numerator unless I absolutely have to if I run into an issue. So right now I'm going to leave this as x minus 1 and the square root of x plus 1. Why? Because I'm trying to simplify stuff. That's why. Now on the denominator, you tell me what do I have to do with this?
Wait a minute, why did I do that? It should be x. Still a problem. Okay, crap. So yeah, then I really don't want to put that in there. X minus 1. Square root of x plus 1. Cancel out. Square root of x plus 1. 1 plus 1, 2. Limit x minus 1 over square root of x minus 1. So x approaches 1. It's 2.
I do have to FOIL or distribute, so that means every term times every term. Tell me, what's square root of x times square root of x? Now, do you see what happens and why we use the conjugate? If you distribute this, we get x, we get plus root x, we get minus root x. What's going to happen with that? That's why we use the conjugate. And then lastly, you're going to get what? You get x minus 1. Do you see why we don't distribute the numerator? If you distribute the numerator, you gotta mess crap up there, right? You have to refactor. It's not going to be easy. If you don't distribute it, the factoring's obvious. The simplification is obvious. What are you going to simplify? Well, at least I hope it's obvious. Is it obvious to you what you're going to cross out? All right, good. Woo. Yeah, kind of obvious. All right. Well, our limit as x approaches 1, notice I'm still writing limit, is this, what do we have left? Are you going to have an issue? Oops. That doesn't look like an X. Are you going to have an issue if you plug in 1? It's not negative, it's positive 1, so we're okay. We have no denominator anymore because we rationalized it. It went away because we were able to simplify it. If we plug in 1, what are you going to get? 2. And that's your limit. How many people feel okay with this so far? Would you like to try 1 on your own? Let's do that. I'm going to give you a little bit more complicated of 1. Not too bad. And if you get stuck on it, no big deal, that's fine, but I want you to at least think about it while you're here. This will be where we end today. So limit as x approaches 0 of the square root of 1 plus x.
Okay, 0 of 0. Do we want to do the conjugate again? So that's 1 plus x minus 1 plus x, square root of 1 plus x. Plus, minus, so these are just going to cancel out anyway, so I don't have to write them. Minus 1 over x plus x plus 1. Okay, I give up.
Minus 1 over x. Are you going to have an issue here? Yeah, I mean, straight up we're going to 0, and that's over 0. That's a problem. So what could you possibly do? Run away. No, yeah, done. No, we're not going to just leave the problem. We can't plug in 0. The only thing you can do here is, what do you think? Can we use that same idea, but only in reverse? Let's try that. Go ahead and do that. Multiply by the conjugate. Conjugates have to have different signs. They have to. It's got to be the same thing on the numerator denominator. It has to. Otherwise, you're not multiplying by 1. And if you're not multiplying by 1, you're changing the problem. You can't change the problem. Also, one more thing I need you to look up here at the board. When you do this, that sign doesn't change. It's only the thing after the square root. So this stays the same. Did you all multiply by exactly that? Do you see how that is the conjugate? We have the square root, whatever that sign is, and then whatever that constant is. And that's what we have here. The square root, the different sign, same constant. Same exact thing. Why you need the same exact thing? In case you're wondering, well, Mr. Leonard, why don't you change that sign as well? What you're trying to do is multiply this in such a way that you actually eliminate the root. So when you multiply this one times this one, the whole entire root goes away, right? The only time you can do that is if the roots are identical. So you can't have different signs, otherwise they're not identical. Hey, which one aren't we going to distribute here, the numerator or the denominator? Don't distribute the denominator. By the way, I'm saving your lives here. If you distribute the denominator, you're going to have to factor it again. That wastes time, so literally.
Wait a minute. So if you Nah, I still don't see it. Never mind.
Really, I'm saving your time, ergo your life. Nice, right? I know I'm such a nice guy today. So on the denominator, I know I'm going to have x and then the square root of 1 plus x plus 1. I'm not going to distribute that. The numerator, yes, you're going to distribute the thing you're trying to rationalize. So if you were to distribute this, why don't you all help me along here? When I distribute this, what's the first expression I'm going to get? 1 plus x. Very good. Okay, and then what?
Minus 1.
So I'm going to get square root of x, square root of 1 plus x, positive. Square root of 1 plus x, negative. That's going to be gone. That's what the conjugate does for you. And lastly, I'm going to get, so this is 1 plus x minus 1. Anything else we can do with that? Anything else? Yeah, combine like terms. What do you get if you combine like terms on the...
Wait a minute. I just saw it. Cancel out the x. I see. Oh, wait, this still has the... Okay, wait, so I can't do that. Now what? Plug in 0, and it works, nice. It's half. Oh wait. Limit x approaches 0, limit as x approaches 0, limit as x approaches 0. Of square root of 1 plus x minus 1 over x equals half.
Numerator. That's kind of nice because 1 and negative 1. And this is why we didn't distribute the denominator, because if you look at that, that's what we're trying to simplify out, right? We're trying to get rid of that. 99% of the time, this works out for you. No, I wrote it backwards, but it doesn't matter. Now that you see the x and x as a factor on the denominator, those things are gone. What's on your numerator, please? Oh, 0 is not on your numerator. What's on your numerator? Come on now, people. 1, yeah. When you cross something out, you don't get a 0. You're actually factoring that out, saying x over x is 1, so you have a 1 up there. By the way, please don't make the intermediate algebra mistake of doing this. A lot of people do this when they're just beginning. They go, oh yeah, I crossed everything out, therefore I have that. Is that true? No, you don't have that. You actually have this. If you forget that, what you're going to end up with is the reciprocal of the answer that you actually want. That's not good. Hey, now can you plug in 0 and be okay? Yeah, even though you still have x on the denominator, look what happens. What's 1 plus 0? 1. Square root of 1? Plus 2? I said 2. I was one step ahead of myself. I'll just write it on the board. There you go, 1/2. Would you raise your hand feel okay with our limits? Good deal. Now you know, we went a long way today. We now know how to evaluate and compute these limits. Next time I'll show you how to do some piecewise limits. I'll show you some trigonometric limits, and then we're off to a fun start. Did you have fun today? Did you have fun today?
Alright, I'm gonna end it there.